had and better not had. Okay, so this is the we call the OLS estimate or of the simple regression model. And remember how we derive this expression. We choose better one and better not so as to minimize the sum of squared residual of the simple regression model. And we derive this expression. Okay. Now the important point is that this beta 1 hat and beta not hat, these are random variable. These are random variable. Why these are random variable? Because they are from a random sample. Okay, if you look at the expression for beta not hat, you have the x1. Okay, so this is the the observation from the random sample i's random sample, and the yi also is the value observation from a random sample. In other words, that this yi and xi data are random. So this observation depends on particular sample you have drawn. Okay, so because the beta 1 hat and beta not hat depends on this particular sample, which are the random values. So that's why the beta 1 hat and beta not hat are random variable. Okay, so what I mean is that when you draw the sample and estimate the slope parameter beta not and beta 1 hat, the estimate value will be different from sample to sample. So that means that this estimate parameter are a random variable. Okay, so that is the key point. That is the key point. Now, because this OLS, we call this is the OLS estimator. You may heard about this OLS, ordinary least square estimator. Why we have OLS? Because we derive this estimator by minimizing the squared residual. So that's least square, minimizing squared residual. It meant by least square. Okay, so that's why we call OLS estimate. Okay, and this has the name because it has something to do with the way we derive this estimator. We derive such that we minimize, in other words, the least square, right? All right. Now, because this estimator, OLS estimator, are random variable, so they have this probability distribution, and also they have a parameter of distribution which are mean and the variance. Okay, so now we have the question that what the estimator beta naught hat and beta 1 hat will estimate on average. Okay, so in other words, what will be the mean of beta naught hat? What will be the mean of beta 1 hat? Or put it another way, what is the expected value of beta naught hat, and what is the expected value of beta 1 hat? And also we will ask another question: what is the variance of beta naught hat, and what is the variance of the beta 1 hat? The beta naught hat, beta 1 hat random variable, so it have mean and variance. So we will talk about the mean, respective mean and variance of these two random variables. So in order to talk about, before we talk about the mean and variance of those OLS estimator, we will make a standard assumption. Standard assumption for the linear regression model. Okay, so we are dealing with the linear regression model. Okay, assumption one, SLR means standard linear regression. Assumption one says that the y and x, the relationship between y and x is linear. Okay, so if you look at this linear model, the says we assume that the relationship between y and x is linear. Okay, so that's the assumption one. We are assuming a linear model. Okay. Second assumption is we draw sample at random. Okay, so when you want to estimate, you have to draw sample at random. Okay, so second assumption is random sampling. Okay, so here are the observation. For example, xi, yi, and the I is the observation 1, observation 2, and observation n. Okay, so it could be household 1, household 2, and household n, something like that. Okay, so we draw the data, and the data is a random sample, which is drawn from the population. Okay, now we will talk about what does it mean, the random sampling. So a little bit talk about, discuss the random sampling. Okay, suppose that the population consists of all workers of country A. So for example, we have the all worker in country like the Vietnam. Okay, the population consists of the all worker in country Vietnam, for example. Okay, now we are assuming that the relationship between the wage or local wage of workers and years of education of worker are linear. Okay, so we are assuming a linear. the relationship in is the linear. Okay, so that was the assumption one. Okay, then the second assumption says we draw completely randomly a worker from the population. So when you draw sample randomly, that means that we do not know beforehand which worker will be drawn. We do not know beforehand which worker will be drawn. Okay, then so you draw a sample at random. Then once you draw a sample, a worker, you draw a worker randomly, then throw back the worker into a population and do the random sampling again. In other words, that the repeat random draw in many times. If you do that, the wage and years of education of the sample worker, it could be n number of workers, will be used to estimate the linear relationship between wage and education. So the point is that we do not know beforehand which worker will be drawn. Okay, so you pick up anyone from the population. Then once you draw a worker, then you have the observation on that workers, then you throw back into population and draw again, then throw back into population and then draw again, and you repeat n times, then you will have the n observation. You will have the observation on independent n work. Okay, so that is how we draw sample randomly. Okay, so so this graph show the data point of the n observation we have from the sample drawn at random. Okay, so for example, here we have the y along vertical and x is along the horizontal. So y measure the wage of workers, and x, for example, measure years of education. Okay, then the first the observation on first worker, we have the data point in here. Okay, so the wage rate is y1 and the years of education is x1. The data point on this ICE worker will be at here. So this is the wage rate of ICE worker and the years of education of the ICE worker. And we have so many data points. And here we have the straight line, which we call population regression function. Okay, and this show the true relationship between the mean of y and the variable x. In this case, we have the slope parameter beta naught and beta 1. This is the population parameter, which we will never know. We will never know unless we survey whole population. Okay, so however, the actual data point deviate from around this the mean, which is the given by this population regression function. Okay. Now, at each data point, you can compute the UI, which is the difference between yi and the value the value on this point, which is the beta naught plus beta 1 x1. Okay, so this is the beta naught plus beta 1 x1 is the point on this population regression function. Okay, and so this yi is the actual yi, which is the actual wage rate, and this point is uh, the wage rate on the population regression function. Okay, so this is the average wage rate. Okay, now then the difference which we call the UI, this we call the error, is the difference between the actual wage and the point. This is the average wage rate given this value of x, okay, in the population. Okay, so the UI is the error term, is the difference between the actual and the average wage in the population. Okay, so some workers earn higher wage than the average wage in the population given this value of x1. Okay, and assumption 3, we assume that there are sample variation in explanatory variable. In other words, if you have the sum of squared of the deviation of xi around its mean, the sum of squared deviation should be positive. It means that xi should vary around its mean. If x does not vary around its mean, in other words, x is constant. In other words, the observation on all workers, suppose that the years of education, all workers are the same 16 years. So the years of education doesn't vary. Okay, so you have the only workers who are educated for 16 years. Then in such a case, we cannot estimate the value of the explanatory variable are not all the same. Okay, if they are same, otherwise they are the same, it would be impossible to estimate how a differential value of the explanatory variable has has different effect on the dependent variable. Okay, so we are trying to estimate the effect of years of education on the wage rate. To estimate, we got to have some variation in years of education, otherwise we cannot estimate. If the years of education same, we cannot estimate. There should be some variation in explanatory variable, and this is the assumption 3. And assumption 4, and this is the very important assumption and the key assumption. Now what it says is the value of exploratory variable must contain no information about the mean of the unobserved factor. Okay, so here the UI is contain unobserved factors, unobserved factor like the ability of workers or intelligence level or family background the worker, which may affect the wage rate, but those factors cannot be observed, and that we call unobservable factors. And this assumption for says is that this unobservable factor error term and exploratory variable, for example, years of education, are independent of one another. In other words, this XI, for example, years of education has nothing to do with the unobservable factor. Okay, that's what this assumption of zero conditional mean says. Okay, so the mean of UI condition on xi should be zero. It means that the x has nothing to do with the UI. X and UI independent, not correlate, independent of one another. And this is the very important assumption, okay, for estimating the slope parameter, okay. And I will tell you later why this assumption is very important. So we have a assumption one linear relationship, assumption two random sampling, and assumption three explanatory variable should vary, and assumption four zero conditional mean. Okay, so those four assumptions. Under this four assumption, we can show this, what this says. Expected value of beta hat is equal to population parameter. And at the same time, expected value of the beta 1 hat equal to population parameter 1. Okay, so this what we call unbiasedness of OLS estimate. Okay, and this is the very important property of the OLS estimator. Because of this unbiased of OLS, we use the OLS method to estimate the regression model. Okay, now what does it mean? Interpretation of unbiased. What does it mean? Sorry about that. Now we know that the estimate coefficient, in other words, beta naught hat, beta 1 hat are random variable. So estimate coefficient may be smaller or larger, depending on the sample. And that is the result of the random draw. Okay, so from sample to sample, you will have a different slope estimate coefficient. Okay, however, on average, the mean of the estimate coefficient will be equal to the value which characterize the true relationship between x and y. and that is this population parameter, beta naught hat, beta 1 hat. Okay, so beta 1, beta naught hat, I'm sorry, the beta naught, beta 1, okay, without hat, okay, beta naught, beta 1 without hat. These are the population parameter, and these are actually unknown. However, we are saying that this parameter characterize the true relationship between y and x in the population. Now, what we are trying to say is that this, on average, the expected value of, okay, that means that on average, the estimate beta naught hat, on average, estimate beta 1 hat will be equal to the true parameter, which is the population parameter beta naught hat, beta naught, and beta 1, okay? So here again, on average means if you repeat sampling, and meaning you draw the sample again and again, and you conduct estimation on again and again and the many times, then you take the average of beta naught hat. You will have the many different value of beta naught hat, and you will have the many different value of the beta 1 hat. However, you take the average of different value of the beta naught hat, you take the average of the different beta 1 hat, then the average value, which means the mean, will be equal to population parameter. That will give you the true relationship. So what it says is, even though when you draw sample one time and estimate, the estimate beta naught hat, beta 1 hat could be away from the true parameter. But when you repeat the estimation, when you draw the sample again and again and repeat and take the average of the estimate coefficient, then on average, the mean of the estimate coefficient will be equal to population parameter. And if that holds, we say OLS estimator is unbiased. And this is the very important property of OLS estimator. And that's why OLS estimator is so powerful, okay? Well, so much for the mean of the estimator. Now we'll talk about the variance of the OLS estimate. Okay. So we said this OLS estimator beta naught hat, beta 1 hat, a random variable. So depending upon the sample, the estimate could be nearer or farther away from the true population parameter. Okay, it happened to be quite close to population value, or it could be far away from the population parameter. Now we want to ask how far we can expect, how far our estimate would be away from the true population value. In other words, we are talking about the variability, okay, the variability, how far away from the true population value. In other words, how much is the variability, okay? Sampling variability, okay? And sampling variability has something to do with that whether the estimate is quite reliable or is not reliable. Sampling variability has something to do with that the estimate is quite precise or not precise. Now, how we measure sampling variance? We measure sampling variance by the estimate of variance, okay, estimate of variance, okay? So we measure the variability by the variance of this estimator. So to find out this variance of the estimator beta naught hat and beta 1 hat, we will make one more assumption, assumption 5. And assumption 5 state that the atom follow the homoscedasticity. Okay, it's a little bit difficult to pronounce. Okay, what does it mean by homoscedasticity? Okay, homoscedasticity means that the variance of, homoscedasticity of the atom means that the variance of atom is constant. It does not depend on the exponential variable. In other words, the value of the exponential variable xi must contain no information about the variability of the unobserved factor. Okay, so what it says is that the variability of the UI, that is the atom, variability of the error, has nothing to do with that the exponential variable. Okay, that's what it says by the homoscedasticity of the atom. Okay, so let me explain using graph. Okay, what does it mean? So we'll have a graphical illustration of the homoscedasticity. Okay, in here we have a in here you see that so we have here the population the regression function, okay, and the actual yi move around this the point on this the mean, which is the population regression function. Okay, now the actual yi move around, and this distribution, how this distribution is spread out, is determined by the variance of the atom. Now, if you look at this graph, how much spread out when x is given by x1, and when x is given by x2, and x is given by x3, how spread out the distribution of this atom, same, okay, same. Whether you have x1, x2, x3, the variability of ui, how much spread out the distribution. If you see the graph, you see that the variance is doesn't depend on this exponential variable. Okay, so that's what it says. Okay, the variability of ui does not depend on xi, which means the variability of ui is constant. What it says. That's what I mean by homoscedastic. Okay, so you see that if you look at this graph, the variability of the distribution of when x is x1 and the variability of this distribution when x is x2 and the variability of distribution when x is x3, it's same, it remains same, constant. Okay, so that's what I mean by homoscedasticity of the atom. Okay. But what if that assumption is not hold? Okay, that what we say heteroscedasticity. Okay, so this is when homoscedasticity assumption is violated. In other words, the variance of the atom depends on the value of the exponential variable. Okay, so if you look at, say, you say the variability of distribution at, suppose that the x1 is 8 years education, and the variability of this is when years of education is 12 and 16. You see, this we have the wage. Okay, so you see that the variability of wage among the worker who has 8 years of education and the variability of wage rate of workers with 12 years of education and the variability of wage rate among workers with 16 years of education. You see that the variability is higher as the years of education is higher. Okay, so maybe this heteroscedastic assumption may be more realistic. You can see that if you look at the wage rate among the elementary school graduate, there is not much difference in wage rate. But if you look at the difference in wage rate among college graduates, you see a lot difference in wage. Okay, so this assumption may be more unrealistic. So heteroscedasticity. Okay. However, for the moment, we will assume this homoscedasticity. Now, later chapters, we will relax this assumption and we will incorporate this heteroscedasticity. Okay, later chapters. Okay, for now, for the moment, for simplification, we will assume that the homoscedasticity of the atom. All right, now, given the assumption 5, which is the homoscedasticity of the atom, then we can derive the expression for the variance of the this OLS estimator, and we can show, but actually we are not going to derive this one is in class. Okay, so this is more a difficult part. So I want to just show that this is the expression for the variance of this OLS estimate. Okay, the first one show the variance of the slope parameter beta 1 estimator, and that is the sigma square divided by this term. We say this total sum of squares. So that is you take the difference between xi and the mean. So this is the deviation of xi from mean, and then you square the deviation, then you sum up over the n observation. Okay, that's what we call total sum of squares. So the variance of the slope parameter beta 1 hat will be equal to the ratio of the sigma square. Sigma square is the variance of the atom nu I. Okay, so that is the population parameter we never know. Okay, but the variance of the beta 1 hat depends on this variance of the atom in the population. So actually this measure the uncertainty in atom. Okay. All right. And on the other hand, the second expression is the expression for the variance of slope parameter beta naught hat, and that is a little bit more complicated. So from the expression, what we can learn, conclusion. So the sampling variability of the estimate regression coefficient, okay, will be higher the larger the variability of unobserved factor. Okay, so that's what it means if we go back to the expression. So this variance of this estimator will be higher when this numerator, which is the variance of the unobserved factor, okay, so which reflect the uncertainty of the unobserved factor. When the value of the numerator goes up, the variance of estimator will go up. Then that makes a lot of sense. When there is a lot of uncertainty in the atom, the estimate will be more imprecise. In other words, you'll have a greater variance of the estimate, okay? And so the sampling variability of the estimator regression coefficient, okay, so beta 1 hat or beta naught hat will be higher the larger the variability of the unobserved factor, which is the sigma square. Second, the lower, okay, the sampling variability of the estimate regression coefficient will be lower. The higher the variation in the exponential variable, okay? So if we go back to the expression, so this denominator is the variability of the exponential variable, variation in the exponential variable, okay? So this denominator is what? The variation in the exponential variable, okay? This is the total sum of squares of variation in x, okay? So this is the denominator. So when this variation in x larger, you can see that the variance of this estimator will be low, okay? So in other words, if you have a large variance in x, then you can have more precise estimate. And also same time, if you look at this formula, if you have a larger sample size, you have a greater number of observations, larger sample size, this denominator will be greater, and as the denominator will be greater, the variance of this estimate are lower, meaning that the estimate will be more precise. So when you have the larger sample size, your estimation will be more reliable. Okay, so that's okay. The variance. Now, next question is how we calculate, because the formula, in order to compute this, we have to know this sigma square. This is the variance of the atom in the population. We never know. Then how we can compute this, the variance of slope parameter. So to compute variance of slope parameter, we have to estimate this sigma square. We have to estimate the population parameter, which is the sigma square. And how we estimate? Okay? So how we estimate, okay? So in here, we assume the homoscedasticity, meaning that the variance of the UI independent of the xi, okay, and constant, okay. So we can say that the variance of ui is constant, the sigma square, okay. The variance of u does not depend on x, so that is equal to what we call the unconditional variance, okay. This is the unconditional variance, okay. Now here the question is, we don't know this sigma square. However, in order to compute the variance of the slope parameter, we have to estimate this because we don't know. So we have to estimate this sigma square. And how we can estimate? Okay, so we estimate using this squared residual. Okay, so this ui, one could estimate the variance of the errors by calculating the variance of the residual. Okay, now what is the residual ui? Ui is the difference between yi and yi hat. Okay, so that is the difference between actual value, for example, actual wage rate, and yi hat. That is the predicted wage rate. Okay, so that is what we call the residual. So the residual tells you how much your regression over predict or under predict. Okay, so that is the difference between the actual yi and the predict yi, whether how much your model over predict or under predict. Okay, so we estimate the population parameter, which is sigma square, using the squared residual. Okay, squared residual. Okay, so we are going to estimate this variance using the variance of residual. Okay, so this is the variance of residual, and usually the expression for the variance is you add up the squared deviation of ui hat from the mean of the ui, then you divide by number of observations. Okay, that's the way we derive the variance. But in this case, we have to be a little bit careful. One more. In this case, you have to divide by 1 over n minus 2. Now, you don't divide by 1 over n. You divide by 1 over n minus 2. Why is that? Because when you divide by 1 over n minus 2, there will be unbiased estimate. When you divide by 1 over n, there will be bias. Okay, so in this case, unbiased estimate of the error variance will be obtained by subtracting the number of estimate regression coefficients from the number of observations. Usually, you divide by number of observations, but in this case, we estimate two coefficients, the beta naught and beta 1 hat, okay? Because we in our regression model, we have a two coefficient to be estimated. That is the beta naught intercept, beta naught hat, and beta 1 hat is the slope parameter. So you use the n independent observation to estimate two parameters. So you lose a degree of freedom by 2. So you have to subtract 2 from the number of observation. Okay, so you have to subtract number of the coefficient. Okay, so how many coefficient we have? Beta naught hat, beta 1 hat. We have 2 estimate. Okay, so you have to subtract the 2 from the number of observations. So in this case, you have to divide by n minus 2. You have to divide by sum of squared residual by n minus 2. That, in that case, this estimate will be unbiased, okay? So by dividing by n minus 2, that estimate will be unbiased, meaning the mean of that will be equal to population parameter. Unbiased means that the mean of, when the mean of the estimator is equal to population parameter, we say the estimator is unbiased, okay, unbiased. Now then we can calculate the standard error of the regression coefficient, okay? Now, when you do your empirical project, you regress your model and you come up with some standard error of your estimate coefficient. And you want to say whether your estimate coefficient is statistically significant. In other words, can be reliable or not. It's a precise estimate or imprecise. To determine, you have to use the standard error of this estimate, okay? You have to have the standard error for this coefficient, okay? Then how you get the standard error of this coefficient, okay? Obviously, standard error is the square root of the variance, okay? Now, in the last page, we have the variance is the ratio of the sigma square divided by the total sum of squared. But in here, instead of the population variance of error term, we plug in estimate, unbiased estimate, sigma hat square for the unknown sigma square. Actually, the variance will be the ratio of the sigma square to SSTX, but we don't know sigma square. So instead of the sigma square, we plug in the estimate the sigma square. And how you get the estimate sigma square, how we get the estimate square, that is this one, okay? That is this one. This is the estimate sigma square, okay? So this is the estimate, that is the u divided by n minus 2. And this is the square sum of the residual, okay? So this is the estimate. So you plug in estimate variance of this error residual for the unknown sigma square. So by plugging the squared residual, you can calculate the standard error of the slope parameter, a beta 1 hat, and also you can calculate the standard error of the beta not hat. Okay, so this, I mean, you don't have to remember this expression because your software program will produce the standard error of the slope coefficient. Okay, but remember that the standard error of the coefficient depends on these two things: how the error term variance of error, and also it depends upon this one, how the variation in the experimental variable, and also it depends on the sample size. The sample size, the greater sample size, you'll have a lower standard error. That means that your estimate beta 1 hat, beta not hat will be precise, can be more reliable. Okay. Okay, so that is the about chapter 2. So you have any question on chapter 2, simple regression model? Okay, so here is the key point is that first of all, how you compute this OLS estimate, okay, how you compute this OLS estimate. And you remember that the OLS estimate is the random variable. So it has the distribution and it has the mean and the variance. And the mean of that is equal to mean of that will be equal to population parameter. That's why I say we say OLS is the unbiased estimator. And we talk about the variance, and the variance is something to do with that the standard error of the estimator and standard error of the estimator tells you how your estimate is, how precise, how much reliable. Okay, so when the error term greater uncertainty, standard error will be higher. When you have a more variation or greater sample size, standard error will be low. Okay, now here the key assumption in this case, remember this assumption. You have this zero conditional mean. Okay, so we talk about this assumption again and again later chapter. Okay, and this assumption assure you that you will have the unbiased estimate. Otherwise, your estimate will be biased. We'll talk about this more in next chapters. Okay, so remember that the error term and explanatory variable are not related. Okay, so this is the very important assumption, to have unbiased estimate. Okay. All right. So I will, if you do not have a question, then I'll take a break and come back. Okay. I will come back. Okay.